Good morning. My name is Errol Sanjaktar. Today I would like to talk about 3D printed polymeric metamaterial recovery behavior after large deformation. I would like to acknowledge my coworker, Ms. Siki Wu. Human-made lattice mechanical metamaterials have recently been shown to exhibit better stiffness or tunable properties than natural materials. Generally speaking, polymeric materials cost less and they are processed easily, and they are predominantly made of light atoms forming long main chains. They have low density and low stiffness. In this work, we demonstrate that body-centered cubic (BCC) polymer-based metamaterials made by 3D printer stereolithography (SLA) display good recovery properties after undergoing cyclic large compressor deformation. Our experimental results reveal that the strut thickness of BCC metamaterials affect the recovery and mechanical behaviors during compression. I would like to summarize our goals. We wanted to explore the mechanical behaviors of polymeric lattice metamaterials with rationally designed structures inspired by natural crystal lattice as BCC unit cell by constituting nodes and struts into unit cell and packing it into three-dimensional structures. Using a commercial desktop additive manufacturing methods through SLA, we fabricated 3D BCC lattice metamaterials with acrylate-based thermoset polymer. We wanted to show that even though acrylate-based thermoset is brittle in bulk form, in lattice structure form it has good recovery and anti-fatigue properties under multiple large compressive deformations. We wanted to elucidate mechanical behavior of a series of different strut thickness BCC lattices to reveal that the lattice metamaterial recovery properties are related to the density of the lattice. The BCC unit cell had a regular hexahedron outer frame and consisted of 12 strut elements in 3 orthogonal directions. It had 8 nodes in the vertices. 4 crossing strut elements connected to each node in diagonal intersect at the center point of the hexahedron cell. This is shown on the figure on the right. Maxwell's stability criteria provided the guideline for frame structures to determine the strut's deformation behavior through calculations of the M value. According to the Maxwell's stability criterion in 3 dimension, M is equal to B minus 3J plus 6. Where J and B are the numbers of joints and bars respectively. The BCC lattice structure keeps M larger than 0 condition, satisfying the stretch-dominated pin-jointed frame. Maxwell's stability criterion distinguishes between the bending-dominated and stretch-dominated cases. Our BCC lattice satisfies the condition M larger than 0, meaning that the metastructure is stretch-dominated. The relative density rho star of the metamaterial is the ratio of lattice density rho with the base material density rho s, and the relations of these, the rho star to the volume and density values are shown in equation 1. We use constant cell wall length L is equal to 5 mm. Strut thickness T sub s varied from 0.3 to 1.4 mm. And the calculated rho star values were from 0.03 to 0.5. The measured relative density for the printed metamaterial samples was higher than the geometric calculation. Such heavier values are attributed to the difficulty in removing all uncured resin sticking to the struts. This situation is shown in the table on the right. Sample preparations all involved an SLA printer, which used a 405 nanometer UV laser beam as the light source. Laser beam will move in the XY plane to follow the 2D layer image submitted. 3D CAD model sequentially produces 50 micron thickness slices in vertical direction. During first layer curing, the plate moves down and keeps 50 micron gap with material stray, and the laser moves to cure the first two-dimensional image. When the first layer is finished, the plate moves up 100 micron gap and lets the fresh resin immerse the gap. The resin kit containing photoinitiator, methyl acrylate-based monomer, and oligomer came from Formlabs company. The combination of these components undergoes polymerization when exposed to UV environment. The figures on the right depict the experimental setup. The one on the far right is the SLA printer, and the schematic to the left of that shows the parts involved in the printing process. After printing, the sample was immersed into isopropyl solvent and placed in an ultrasonic shaker for removing any uncured resin. The tensile test sample for the base material test was prepared by SLA process, printing the ASTM D638 type 4 dog bone samples, which were tested under 5 mm per minute extension rate. The compression test samples were 50 cubic millimeter samples simulating the lattice structure, and these were tested under compression. And 3D printed samples were also prepared to use in dynamic mechanical analysis. The 10 delta peak temperatures was used as the base material's glass transition temperature. We performed cyclic compression tests on the metamaterial lattices. The compression force was applied in the plane perpendicular to the build plate in 3D printing. Using 5 mm per minute testing at room temperature, we obtained maximum strain level up to 60%. After each loading-unloading cycle test, we waited 24 hours for samples to relax between two compressive cycle tests. We first measured the base material properties for under both tensile, DMA, and also compressive cases. The bulk tensile sample had 5.5 to 2% elongation at break. The TG was around 80 degrees C. The tensile modulus was calculated as 2 gigapascal using the initial linear elastic region. The compressive modulus was measured as 560.5 megapascal. As far as cyclic tests, when the 0.3 millimeter strut thickness sample was compressed to 60% strain, the first stress-strain response exhibited multiple yield peaks and had higher stiffness with high yield strength, but the consecutive yield peaks decreased with continuing deformation. So the elastic modulus also decreased, as shown in the graph on the right. At the termination of relative horizontal plastic region, the stress increased steeply by final densification. The final equilibrium elastic modulus decreased to 0.6 megapascal, which is 0.1% of the original modulus of 560.5. This situation is shown in the graph with the arrow. You can see that by the time we reach 3 cycles, this condition is reached. So we have an initial abrupt monotonic decrease in the elastic modulus. It then levels off, reaches a plateau, and decreases mildly as we increase the cycles to 10. The condition that I described related to the yield stress is shown on this graph on the right. You can see that the first cycle of this compressive stress-strain curve has a relatively high yield stress, and then we have additional small peaks. When we go to the second cycle, the yield stress is reduced, and the subsequent peaks have disappeared. We measured the sample size in 3 dimensions before and after the cyclic tests. The size change was found to be less than 10%. As a result of our cyclic tests, we think that the 0.75 millimeter strut thickness represents an approximate transition value from recoverable to irrecoverable behavior after 60% compressive strain based on stiffness. This behavior is shown on the table on the left. As far as the failure mechanisms are concerned, we can consider 3 different failure mechanisms during compression. We have elastic buckling based on Euler's theory, plastic yielding collapse, and brittle fracture. The stress concentration can lead to brittle fracture or plasticity leading to permanent deformation, but potentially a recoverable elastic buckling occurs in metamaterials when the necessary stress is below the critical stress sigma Fs required for parent material to fracture. We consider the critical limitation Ts over L from the Euler's theory when corresponding to sigma buckle equal to sigma Fs, which means that below the Ts over L limit critical line, the Euler buckling stress is lower than the fracture stress corresponding to elasticity buckling. The calculated strut thickness limit was 0.781 millimeter, based on as calculated by equation 2. This compared well with the phenomena we observed experimentally when T over L was larger than 0.075. After T equal to 0.781 millimeter, the brittle mechanism dominates the plateau region. As far as the relationship between modulus and density is concerned, the lattice deformation is regarded as stretch-dominated, leading to higher strength and stiffness due to no intrinsic bending deformation of the truss structure. In this case, the ideal stretch-dominated structure scale linearly with E over ES, which is equal to rho over rho S, and sigma S over sigma YS, approximately equal to rho over rho S. Our BCC lattice satisfies the condition M is larger than 0, meaning that the metastructure is stretch-dominated. For our BCC lattice metamaterial in linear quasi-elastic deformation, the modulus and strength follow a power law scaling with relative density where E is approximately equal to rho star times 1.57 and sigma Y is equal to rho star times 1.86. The traditional forms usually have E is equal to rho star squared for open cell structures. According to the Maxwell stability equation, our BCC metamaterial should belong to the stretch-dominated group with the exponent n is equal to 1. But our experimental results show that the exponent in n is between 1 and 2, as shown in the graph on the upper right. Therefore, theoretically, the BCC structure has better performance in low power, low scaling than natural open cell, but the discrepancy still exists with theoretical stretch-dominated structure scaling lows. Such a deviation could be partially explained by the imperfect SLA printing process. So in conclusion, we can say that we have a good reversible performance in 3D printed polymeric BCC lattice metamaterials. The design concept was inspired by a common natural crystal lattice structure. In order to demonstrate the recovery properties, we tested a series of strut thickness samples using the same base material and structure. Thinner cell walls were beneficial to recovery. When the cell wall thickness reached a critical point, irreversible fracture occurred. The shape and modulus recovery ability decreased with cyclic compression. The thinner struts provided good recovery and anti-fatigue properties. For large thickness and density metamaterials, the resins were hard to remove from the struts, caused the weight to be heavier than it should be, and apparently the density was also higher. So the E versus rho star to the n slope was smaller than expected. During the printing process, the geometry was not totally in accord with the CAD model, especially in strut juncture locations. Such deviations are expected to change the strut's mechanical behavior during loading. This will also affect the power law scaling and cause it not to agree with the prediction. Thank you very much for your attention.